Welcome to Cosmic Sedation, where the stars whisper you to sleep. Tonight, we explore the mysterious chill of space amidst the sun's fiery embrace. Subscribe and like if you're ready to dive into the cosmos with us. Your questions fuel our journey through the universe. As the night unfolds, let's drift together into the vast, cool expanse of space. Here we go, gently easing into the night. At minus 270 degrees Celsius, the temperature in deep space is colder than any naturally occurring place on Earth. Yet, just 150 million kilometers away, our sun burns at a staggering 5,500 degrees Celsius at its surface and reaches temperatures of over 15 million degrees within its core. This paradoxical coldness of space contrasts sharply with the intense heat of stars. The vast emptiness between celestial bodies is so sparse that it barely interacts thermally, allowing for this extreme chill to persist. Stars like our sun emit radiation through a process called nuclear fusion. In their cores, hydrogen atoms collide at such high velocities that they merge into helium, releasing enormous amounts of energy in the form of light and heat. This reaction powers stars for billions of years, yet it doesn't warm the space around them significantly. Space is nearly empty. On average, there are only about 1 atom per cubic centimeter between stars. The particles in this interstellar medium move too slowly to transfer much thermal energy. Consider Earth's atmosphere, a thin layer that keeps our planet from experiencing such extreme cold. In space, without an atmosphere or any significant matter to absorb and redistribute heat, the sun's radiation is spread thinly across vast distances. For instance, it takes 8 minutes for light from the sun to reach us, traveling at 300,000 kilometers per second. This journey means that by the time solar energy reaches distant planets or spacecraft, it's distributed so widely that its effects are negligible. The temperature in space is not a uniform minus 270 degrees Celsius everywhere. It varies depending on proximity to stars and other celestial bodies. Near Jupiter's moon Io, for example, temperatures can fluctuate dramatically due to volcanic activity. However, far from any star or planet, the cosmic microwave background radiation, leftover heat from the Big Bang, keeps space just above absolute zero at minus 270 degrees Celsius. This faint glow is detectable across all directions in the universe. Humans exposed to such extreme cold would experience rapid cooling of their skin and vital organs, leading to hypothermia within minutes. Yet, paradoxically, if a person were to enter an environment with no air or heat source nearby, they might initially feel warmer due to body heat escaping into space through radiation. The human body can only maintain its internal temperature for about 30 minutes in the vacuum of space before irreversible damage occurs. To understand why space remains so cold despite the sun's immense energy output, consider this. The total amount of energy emitted by all stars combined is spread out over an incomprehensibly vast area. Our galaxy alone contains hundreds of billions of stars, and each star emits light that travels in all directions. This means that even though our sun produces enough energy to warm Earth significantly, it has no noticeable effect on temperatures millions or billions of kilometers away. The process by which stars emit radiation and space remains cold is further exemplified by the life cycle of a star like our Sun. Stars are born from clouds of gas and dust, known as nebulae, where gravity causes these particles to collapse into dense regions that eventually ignite nuclear fusion. Once a star begins fusing hydrogen in its core, it radiates energy outward, but this energy is not evenly distributed across the universe. Instead, it travels in straight lines through space until it encounters another celestial body or is absorbed by distant planets and moons. For instance, Earth receives only about 1/1000th of the Sun's total output due to our relatively small size and distance from the star. This minuscule fraction of solar radiation warms our planet sufficiently to sustain life. In contrast, most of the Sun's energy escapes into the vast emptiness between stars, where it is quickly diluted over unimaginable distances. To put this in perspective, if you were to place a small light bulb at the center of a sphere with a radius equal to the distance from Earth to the nearest star, about 4.25 light years, the amount of light reaching any point on that sphere's surface would be incredibly faint, far too dim for human eyes to perceive without specialized equipment. This same principle applies to stars across the cosmos. Their radiant energy is spread so thinly over such vast expanses that space remains a near absolute zero environment. Even as our Sun continues its life cycle, fusing heavier elements in its core and eventually expanding into a red giant, it will still not significantly warm the interstellar medium. The radiation it emits simply lacks the density of particles needed to transfer heat effectively over cosmic distances. This process underscores how the coldness of space is maintained despite the fiery brilliance of stars like our Sun. At -270 degrees Celsius, deep space is colder than any naturally occurring place on Earth. Yet, despite this extreme cold, cosmic microwaves fill every cubic meter of the universe with a faint, ancient radiation. This electromagnetic remnant from the Big Bang permeates all of space, yet contributes less heat to our environment than a single snowflake falling in Antarctica. These microwaves are remnants of the early universe's colossal energy release, now cooled to an average temperature of 27 Kelvin. They originated approximately 13.8 billion years ago, when the universe was only 380,000 years old, before even atoms had formed. Today, they provide a uniform background radiation that is slightly warmer in some directions than others, reflecting the early density variations from which galaxies and stars would eventually coalesce. For an observer floating in deep space, this radiation would feel like an almost imperceptible touch of warmth on their skin. Remarkably, these cosmic microwaves are not evenly distributed, but carry subtle temperature fluctuations that can be measured to a precision of about 1 part in 100,000. These variations trace back to the quantum fluctuations in the early universe and serve as the first seeds for all structure we see today. The human body, with its core temperature around 37 degrees Celsius, would register this microwave radiation only if equipped with highly sensitive instruments. Otherwise, it remains undetectable by our senses. This uniformity across vast distances underscores the interconnectedness of the cosmos. Every cubic meter of space contains a faint echo of the universe's birth. While cosmic microwaves are pervasive throughout the universe, their contribution to heating any given volume is negligible compared to other sources like starlight or solar radiation within our own galaxy. In fact, if you were to travel far from the Sun and its immediate neighborhood, these microwaves would be the only thermal source in your vicinity. Yet, despite their omnipresence, they add less heat than a single photon emitted by an average light bulb on Earth. This paradox highlights how profoundly different conditions are between our familiar environment and the vast reaches of deep space. The energy density of cosmic microwave background radiation is equivalent to about 460 photons per cubic centimeter at its peak wavelength of approximately 1 millimeter. Each photon carries a minuscule amount of energy, far too little to significantly warm anything it encounters unless accumulated over immense timescales or in extremely large volumes. This uniformity and minimal heat contribution challenge our intuition about what constitutes warmth in the universe. It serves as a reminder that even in environments where temperatures are near absolute zero, there can still be an active presence of energy. As we consider the journey of these microwaves from their origin at the dawn of time to their current state, filling every corner of space, it becomes clear that they have been traveling for nearly 14 billion years. Each photon has traversed distances so vast that light itself takes billions of years to cross them. When observed through radio telescopes on Earth, these ancient photons reveal patterns and structures that would take billions more years to fully develop into the galaxies we see today. In this context, cosmic microwaves are not just a remnant of the past, but also a profound window into the future evolution of the universe, offering insights into processes that will unfold over incomprehensible timescales far beyond human lifetimes. In the void between stars, where temperatures drop to minus 270 degrees Celsius, photons from our Sun embark on a paradoxical journey. These particles of light, traveling at 300,000 kilometers per second, traverse an environment colder than any naturally occurring place on Earth. Yet, despite this frigid vacuum, they retain the energy born in the heart of their star. This journey through coldness is not just a passage, but a testament to the ineffable nature of space. Each photon's path is unique, weaving around cosmic dust and molecular clouds that dot its trajectory. As it moves, it encounters vast expanses where no heat source exists to warm the void. Yet, paradoxically, these same particles can eventually reach Earth at a speed that ensures they are still capable of heating our planet. This journey from the Sun's surface to Earth is an interstellar relay race through a freezer, yet one that maintains its energy over millions of kilometers. The photon's passage is a delicate balance between creation and destruction. On their way, some collide with atoms in space, briefly changing course or even being absorbed, only to be re-emitted. This process is akin to the journey of a traveler who stops at various points along the road before finally reaching their destination. The energy within each photon remains constant throughout its voyage, ensuring that when it reaches Earth, it bears the imprint of the Sun's fiery birth. The temperature gradient between the source and destination of these photons is astonishingly vast. Imagine a scenario where an object starts at a searing 5,500 degrees Celsius and ends up in an environment colder than minus 270 degrees Celsius. This dramatic shift underscores not just the physics of space, but also the resilience of light itself. The coldness of deep space does not merely exist as an absence of heat. It is a force that shapes the journey of photons, ensuring they are undiluted by their surroundings. Upon reaching Earth, these photons interact with our atmosphere, initiating a cascade of energy transfers. They collide with molecules and atoms in the upper layers, gradually losing some of their energy through scattering and absorption. This process mirrors the way heat moves from a hot object to its cooler surroundings, but it happens on an astronomical scale. The cooling effect of space is so profound that it can be felt even by the light that reaches us, as each photon's journey ends in a gentle warmth compared to its fiery origin. This journey of photons from the Sun to Earth encapsulates the paradoxes inherent in our universe. While deep space remains perpetually cold, the energy carried by these particles ensures life on Earth is possible. Each photon's path through the vacuum serves as a reminder that even in the coldest reaches of space, there exists an unyielding connection between stars and planets. This delicate balance allows for the continuous flow of light and warmth from distant stars to the worlds they illuminate. The photon's journey through this near-absolute zero environment is not a passive glide, but an active negotiation with the cosmos itself. Each photon encounters clouds of hydrogen and helium, remnants from the Big Bang, which scatter some of their energy in unpredictable directions. These collisions occur at intervals that are infinitesimally brief, yet crucial for understanding how light travels through space. The probability of interaction between a photon and a particle of gas is so low. On average, one collision every trillion kilometers, that the vacuum seems almost transparent to our eyes. Yet, these rare encounters ensure that the photon's energy is subtly modulated as they travel, like a traveler who occasionally pauses to exchange tokens with passers-by along their route. This process introduces an element of chance into what might otherwise be seen as a perfectly predictable journey. The path taken by each photon becomes slightly altered over time, influenced not just by its initial direction, but also by the random encounters it has in the vastness of space. On Earth, this variability is imperceptible to us. We see the Sun as an unchanging source of light and warmth. But for those photons that do reach our planet after such a long journey, their arrival is marked by a subtle shift in energy. They have traversed a realm where temperatures are lower than anywhere found on Earth, yet they still carry enough energy to warm our skin and fuel life's processes. This paradox of light traveling through an environment colder than anything we can experience underscores the interconnectedness of all things in the universe. The same forces that keep space so cold also ensure that these photons retain their ability to bring warmth and illumination to distant worlds like ours. Each photon's path is a thread in the complex fabric of cosmic interactions, weaving together the Sun's radiance with Earth's atmosphere in an intricate dance across time and distance. As particles stream from the Sun's corona at an astonishing speed of up to 800 kilometers per second, they carry with them the heat and energy generated by our star's nuclear furnace. The solar wind, a continuous outflow of charged particles, expands into interstellar space like an inflating balloon. At first, this flow remains relatively dense and maintains a temperature that rivals the sun's surface, around 5,000 degrees Celsius. Yet, as these particles journey further from their origin, they encounter vast stretches of empty space where collisions become increasingly rare. This isolation leads to a phenomenon known as adiabatic cooling. The expansion causes each particle to spread out over a larger volume without gaining or losing heat through external interactions. Consequently, even though energy is conserved within this system, its distribution becomes more diffuse, leading to a significant drop in temperature. It's akin to blowing up a balloon. While the total air mass remains constant, the pressure inside diminishes as the balloon expands. In an environment where 1 cubic centimeter of interstellar space contains no more than a single atom on average, these particles are effectively alone. Their journey through this near vacuum is marked by an exponential decrease in temperature and density. By the time they reach the heliopause, the boundary between our solar system and true interstellar space, these once-energetic particles have cooled to a mere few tens of degrees above absolute zero, minus 273 degrees Celsius. This cooling process underscores the remarkable efficiency with which energy dissipates over vast distances in deep space. The temperature drop in these expanding particle clouds is not just a matter of distance, but also relates to the age-old principle that energy seeks equilibrium. As particles from our Sun travel through interstellar space, they gradually lose their kinetic energy due to their increasing separation and minimal interactions with other matter. This cooling process mirrors the way heat escapes a warm object left in a cold room. The rate at which this happens is inversely proportional to the density of surrounding particles. In the sparse medium of deep space, where encounters are infrequent, it takes millions of years for these particles to reach thermal equilibrium with their surroundings. An intriguing paradox emerges when considering the vast distances involved. Despite originating from a source that burns at millions of degrees, solar wind particles experience a cooling effect so profound that they eventually become colder than even the coldest known places on Earth. This cooling process is not only a testament to the expansive nature of space, but also serves as a reminder of how quickly energy can be dispersed when faced with near-infinite space. Each particle's journey is an individual story of thermal isolation, where distance itself becomes both the cause and the consequence of their cooling. Meanwhile, this cooling process has profound implications for the cosmic environment beyond our solar system. As these particles cool, they contribute to the intricate web of magnetic fields and plasma that permeates interstellar space. This cooled material plays a crucial role in shaping galactic structures, influencing star formation, and even contributing to the composition of new stars and planets. The cooling of solar wind particles thus serves as a bridge between our local environment and the broader cosmos, illustrating how processes on one scale can have far-reaching effects across astronomical distances. At the very beginning of time, when the universe was just 380,000 years old, it was filled with an incandescent plasma. The temperature then was approximately 3,000 Kelvin, a luminous glow that would have been visible across every wavelength if there were eyes to see it. This period marks the cosmic dawn, a moment when light first streamed freely through space. Today, deep space has cooled dramatically, reaching temperatures as low as -270 degrees Celsius. Yet this cooling process is not uniform. It unfolds over billions of years, dictated by the expansion and thinning of the cosmos. The universe's temperature decline mirrors its gradual cooling from an intense initial state to a distant future where even stars will fade. Consider now the lifespan of a star like our Sun, which is approximately 10 billion years long. In this cosmic timeline, the cooling of space occurs at a pace that dwarfs human comprehension. When the universe was young and hot, stars were born rapidly, their fusion reactions igniting in dense clouds of gas and dust. These stars burned brightly, radiating energy into the expanding void. Yet, as time progresses, fewer stars are formed, and those that do burn out eventually. The cooling of space is a testament to this slow decline in stellar activity, illustrating how the universe transitions from its fiery birth to an eventual cold death. This process takes billions upon billions of years, far beyond any human lifespan, yet it shapes every star's fate, including our own Sun. The cosmic microwave background radiation, or CMB, offers a snapshot of these ancient temperatures. It is the afterglow of the Big Bang, now stretched to microwaves by the expansion of space itself. This radiation permeates all of space, uniformly filling the universe with a faint glow at -270 degrees Celsius. Despite being so cold, it holds within its spectrum the echoes of the early moments when the universe was hot and dense. The CMB is a relic from an era when the first stars lit up the cosmos, their light now reaching us as microwaves. This radiation underscores how time has stretched out the once tiny universe into the vastness we observe today. In contrast to this deep cosmic chill, stars like our Sun generate temperatures in their cores that can reach over 15 million degrees Celsius through nuclear fusion. The energy from these reactions is then radiated outward as heat and light, warming planets within a star's vicinity, but cooling further as it travels into the void of space. This paradox of extreme heat at stellar centers and frigid depths of space highlights how the universe operates on multiple scales simultaneously. For instance, while Earth enjoys warmth from solar radiation, that same energy gradually dissipates, contributing to the overall cooling trend of the cosmos. The Sun's radiant energy is both a local source of life-giving warmth and part of the larger cosmic cooling process. The temperature gradient between stars and deep space also influences the formation of new celestial bodies. Gas clouds in interstellar space, which are relatively cold compared to stellar interiors, can collapse under gravity to form new stars or planets. This process, known as star formation, relies on the contrast between hot stellar cores and cooler surrounding regions. As these clouds cool further due to expansion, they become more stable, leading to a slower rate of starbirth in later stages of cosmic evolution. In this way, the temperature difference plays a crucial role in shaping the structure of galaxies over time. As we gaze into deep space, we are witnessing an ancient cooling trend that has been underway for billions of years. The universe, once a seething plasma, is now on its way to becoming a cold expanse dominated by dark matter and energy. Our sun will eventually join this cooling process, expanding into a red giant before collapsing into a white dwarf, a cold remnant of what was once an active star. This journey from birth to death, from extreme heat to eventual chill, is mirrored in the broader evolution of all stars within galaxies across cosmic time. The universe's temperature history encapsulates both the energetic beginnings and the inevitable cooling fate of every star, including our own. In the vacuum of deep space, where matter is as sparse as it can be, heat transfer occurs not through conduction or convection, but rather through radiation. Each cubic meter contains fewer than one atom on average. This near-total absence of particles means that heat must travel across vast distances solely via electromagnetic waves, a process far less efficient than the direct collisions found in denser environments. Imagine standing at sea level on Earth, where air molecules are packed tightly together. Your body loses heat through conduction to nearby air molecules. But out here, there's almost nothing for your hypothetical spacesuit to transfer its warmth to. This vacuum acts as an insulator of sorts, trapping any heat within objects rather than allowing it to dissipate freely. A surprising parallel exists on Earth. The technology used in thermos flasks operates similarly, using a vacuum layer to prevent thermal energy from escaping. Consider the boiling point of water under these conditions. At sea level, water boils at 100 degrees Celsius. However, in the vacuum of space, it would vaporize instantly due to the lack of atmospheric pressure. This rapid phase change is known as sublimation, where a solid turns directly into a gas without passing through the liquid state. The absence of air resistance also means that any object exposed to sunlight will experience dramatic temperature fluctuations between its sunlit and shadowed sides. Despite these extreme conditions, spacecraft engineers must carefully consider how materials interact with such a hostile environment. For instance, the surface of the International Space Station can reach temperatures as high as 120 degrees Celsius in direct sunlight and plummet to minus 150 degrees Celsius when shaded by Earth or its own structures. This wide temperature swing underscores how effectively the vacuum isolates different parts of an object from each other. It's akin to wrapping a hot potato in plastic wrap. While it prevents heat loss, it also traps warmth inside. To maintain functionality and avoid structural damage caused by these extreme temperature variations, spacecraft often incorporate multi-layer insulation blankets. These layers are designed not only to reflect radiant heat back onto the surface, but also to provide an additional barrier against micrometeoroids and space debris. Each layer adds complexity, yet the principle remains straightforward. Reduce the number of particles that can transfer energy in or out. Intriguingly, this vacuum-induced isolation also plays a role in cosmic phenomena beyond spacecraft design. For example, planets like Pluto orbit so far from the Sun that they receive very little radiant heat. Yet, Despite their cold temperatures, these distant worlds retain some internal warmth due to residual heat left over from their formation billions of years ago. This leftover energy, trapped within the planet's core by its own material properties and the vacuum of space, slowly radiates away into the cosmos. Thus, the very emptiness that defines space also serves as a container for ancient thermal memories encoded in distant worlds. The sparse distribution of particles in space means that even when photons from distant stars do manage to travel across light years to reach us, their journey is an unfathomably long and lonely one. Each photon must navigate through a near-total void, encountering obstacles so infrequent that the average path between collisions would span trillions upon trillions of kilometers. This staggering distance means that these particles of light often complete their entire voyage without ever interacting with another atom or molecule along the way. In contrast, think of walking down a bustling city street. Every few meters, you might bump into someone or brush past an object. Now imagine traveling for thousands of miles through a completely empty landscape. This is what it's like for photons traversing deep space. This rarity of interactions also explains why the vacuum acts as such an effective barrier against heat transfer. Without particles to carry away thermal energy, objects in space retain their warmth or coldness far longer than they would on Earth. For instance, consider a spacecraft orbiting Mars during its night-side passage. Despite being close enough to feel some radiation from the sun and other celestial bodies, the extreme emptiness around it ensures that heat loss occurs almost exclusively through radiative cooling. This process takes time. The spacecraft's materials slowly cool by emitting infrared light into the surrounding vacuum rather than losing energy through collisions with air molecules as they would on Earth. The result is a gradual temperature drop over hours or even days, depending on factors like insulation and exposure to cosmic radiation. Meanwhile, back in our solar system, planets and moons have their own unique thermal histories shaped by this interplay between distant light sources and the cold vacuum that envelops them. Every celestial body has its own story of warmth and cooling etched into its surface over billions of years, a testament to how deeply space's emptiness influences everything it touches. In the vacuum of space, without protection, an astronaut would experience temperatures plummeting to minus 270 degrees Celsius within minutes. The human body, designed for Earth's atmosphere and gravity, cannot withstand such extremes. This cold is not just a temperature, but a condition where heat leaves the body faster than it can be produced. Each molecule in the skin radiates away its warmth directly into space, without any medium to slow or buffer that loss. At this temperature, water would freeze instantly upon exposure, and yet, paradoxically, no frostbite would occur immediately. The vacuum's lack of pressure means that blood could boil internally if not for a spacesuit's pressurization. This boiling effect occurs because the liquid in bodily fluids reaches its boiling point at minus 270 degrees Celsius under such low pressures. It is akin to being caught between two extremes, the relentless cold and the sudden vaporization of life-sustaining liquids. The space environment strips away all forms of insulation, leaving the astronaut's body vulnerable to a process known as sublimation, the direct transition from solid to gas without passing through liquid form. If skin were exposed for even moments, it would begin to lose moisture at an alarming rate. This dehydration is not gradual, but occurs with startling speed, illustrating how space can strip away life's most basic elements almost instantly. Space's coldness, however, is not merely a passive environment. It actively seeks out warmth. In the absence of air or water, any heat source in space radiates into the void without hindrance. The astronaut would feel this as an insistent pull of their body's energy outward. This radiation is relentless and unyielding, much like the way sunlight can warm a dark surface on Earth, only to have that warmth dissipate once the sun moves away. In space, there is no such warming phase. The human body in this environment would also experience a curious phenomenon known as freezing without ice. At minus 270 degrees Celsius, tissues would freeze solid, but with an unusual texture due to the absence of liquid water to form typical ice crystals. This process, while quick, does not cause pain because the nerve endings are numbed by the cold long before they can register discomfort. Yet, this freezing is a precursor to more profound changes. Cells could rupture from internal pressure as liquids vaporize and tissues become brittle. In the vastness of space, even light itself behaves differently. Photons travel through the vacuum at incredible speeds, but in the context of human exposure, their energy would be insufficient to warm an unprotected body. The cold is not just a lack of heat, it is also the absence of any significant radiation that could provide warmth. This stark reality underscores how space's coldness is as much about the vacuum's emptiness as it is about its temperature. In this environment, the astronaut's breath would become an almost visible reminder of life's fragility. Without a spacesuit, exhaled air would instantly condense and freeze into tiny ice crystals, sparkling briefly before dissipating into the void. This momentary display of vapor is a stark contrast to how such moisture behaves on Earth, where it might linger as fog or mist. Each breath taken in space would be an act of defiance against the encroaching cold, yet each exhalation contributes to the body's inevitable cooling. The human circulatory system, designed for warmth and pressure, would struggle under these conditions. Blood vessels constrict to conserve heat, a reflexive action that paradoxically accelerates the freezing process in exposed areas. This constriction also limits blood flow to extremities, potentially leading to loss of sensation and function. In space, even survival instincts like shivering are futile. There is no air to warm or insulate, rendering such physical responses ineffective. The spacesuit, when worn, becomes a life-sustaining cocoon that must counteract the relentless cold. It uses layers of insulation and heating systems to maintain a body temperature environment inside. Without this protection, the astronaut would face not just freezing, but also an increased risk of decompression sickness due to nitrogen bubbles forming in the bloodstream as it vaporizes. This dual threat, extreme cold coupled with internal pressure changes, underscores the delicate balance required for survival in space. The human body, evolved for a planet where warmth and atmosphere are taken for granted, finds itself utterly unprepared for the harsh realities of the void. Yet within this extreme environment, there is an eerie beauty. The stars, distant suns that appear as pinpricks of light, offer no warmth but do provide a serene backdrop to the silent struggle against the cold. Each star represents a fusion reactor, generating energy and heat on scales unimaginable to human experience. Yet their light reaches Earth after traversing billions of kilometers, diminished and powerless to warm an unprotected body in space. In the near-zero temperatures of deep space, particles behave in ways that defy our everyday expectations. Here, atoms and molecules drift far apart, their interactions reduced to infrequent collisions. At -270 degrees Celsius, which is just 3 Kelvin above absolute zero, the kinetic energy of these particles approaches its minimum possible value. Remarkably, this environment contrasts sharply with the bustling atomic activity within stars like our Sun. In space's vacuum, atoms rarely collide, leading to a kind of stasis where particles barely interact. This sparse interaction rate means that heat transfer occurs almost exclusively through radiation rather than the collisions common on Earth. Yet, in the heart of stars, temperatures can reach millions of degrees, driving rapid atomic interactions and fusion reactions. The coldness of space thus serves as a stark reminder of how profoundly different conditions can dictate particle behavior. As we consider this environment, it's worth noting that even at these extreme low temperatures, particles don't completely cease their motion. Quantum mechanics dictates that all matter possesses intrinsic energy, known as zero-point energy. This phenomenon ensures that atoms never fully stop moving, no matter how cold they become. In deep space, the quantum jitters of particles are the sole source of any detectable activity. This subtle movement means that in theory, given enough time, these particles could eventually collide and interact. To understand this better, imagine a scenario where you place an object at absolute zero temperature. Atoms would be as still as possible, yet not entirely motionless due to quantum fluctuations. In the vast emptiness of space, these tiny movements are amplified by the sheer volume. If we were to observe particles in deep space through a powerful telescope, what we'd see is an almost imperceptible dance, a ballet of atomic jitter that defies the notion of complete stillness. The sparse particle density and minimal interactions in space have another intriguing consequence. It slows down time for these atoms according to Einstein's theory of relativity. Time dilation occurs due to the relative motion between particles, even at near-zero temperatures. This effect is incredibly minute, but underscores how profound physical principles can manifest in such an environment. The slower passage of time for these particles highlights a paradox where extreme coldness paradoxically stretches the fabric of time. In this context, it's also worth considering what might happen if we could somehow introduce warmth into deep space. Injecting heat would rapidly increase particle collisions and interactions, creating a cascade of activity that contrasts sharply with the current state of near stasis. This scenario illustrates how delicate the balance is between absolute coldness and atomic activity. Yet, in our observable universe, such a dramatic shift remains hypothetical. as no known process can significantly alter the temperature distribution across vast cosmic distances without significant energy input. In this environment of profound stillness, the particles that do collide occasionally are doing so at velocities barely above zero. These interactions are so rare that they occur on timescales far beyond human comprehension, trillions upon trillions of years between each fleeting encounter. Each collision is a microscopic event, releasing infinitesimal amounts of energy as photons, which then scatter into the void. The average distance a photon travels before encountering another particle in deep space can exceed millions of kilometers. This vastness underscores how utterly isolated these particles are, existing in a state of near-perpetual solitude. Remarkably, this isolation is not entirely devoid of consequence for human understanding. In laboratories on Earth, scientists have managed to create conditions that approach the coldness of deep space through cryogenics and advanced cooling techniques. These environments, known as dilution refrigerators, can reach temperatures just a few billionths of a degree above absolute zero. Here, atoms behave in ways that mirror their counterparts in deep space, offering insights into quantum phenomena and the nature of matter at its most fundamental level. The parallels between these earthbound experiments and the conditions in outer space illustrate how controlled environments on our planet can serve as microcosms for cosmic processes. In both instances, the minimal interaction rates allow scientists to study particle behavior with unprecedented precision, revealing details about quantum mechanics that would be obscured by more energetic systems. Yet, despite the similarities, there remains a fundamental difference. While lab-created coldness is fleeting and carefully managed, deep space maintains its near-zero temperatures across billions of light years, untouched by human intervention. This vast cosmic expanse serves as an eternal laboratory where particles continue their slow, deliberate dance through eternity, governed solely by the laws of physics. On Earth, the atmosphere acts like a blanket, trapping heat and keeping our planet habitable. The greenhouse effect warms us by absorbing infrared radiation emitted from the surface and re-emitting it back down. In contrast, space lacks this protective layer, allowing objects to radiate their thermal energy away freely. Consider Venus, with its thick, toxic atmosphere that traps heat so effectively. Its surface temperature reaches a scorching 460 degrees Celsius. Meanwhile, in deep space, the lack of such a blanket means temperatures plummet as low as -273 degrees Celsius. This stark difference underscores why our planet remains temperate despite being bathed in the sun's radiation. The Earth's atmosphere is composed primarily of nitrogen and oxygen, which absorb infrared radiation efficiently. In space, however, molecules are too sparse to interact effectively with heat energy. If a spacecraft were to release heat into this environment, it would radiate away without encountering any significant obstacles. This process explains why the International Space Station must actively manage its internal temperature. Imagine stepping outside on a clear night in the Arctic, where temperatures can drop below -30 degrees Celsius. Your body feels cold because you're losing heat to the surrounding air. In space, astronauts wouldn't experience this gradual cooling. Instead, their spacecraft would need to maintain warmth artificially. This environment is so effective at dissipating heat that any exposed surface quickly becomes extremely cold. The sun's energy travels through space as electromagnetic radiation, a process unaffected by temperature differences in its path. Once the photons reach Earth, they interact with our atmosphere and surface, warming us. In the vacuum of deep space, however, objects can cool to near absolute zero, almost instantaneously if not protected. This rapid cooling occurs because there's no medium for heat conduction or convection. Only radiation exists as a method of energy transfer. To understand this better, consider how spacecraft must be designed with multiple layers to insulate against the cold of space. These materials prevent the internal warmth from radiating away too quickly. Paradoxically, while the sun emits vast amounts of energy in all directions, its photons can travel billions of kilometers before encountering anything substantial enough to absorb or reflect them. This phenomenon highlights how effective space is at dispersing heat, making it an utterly inhospitable environment for anything not equipped with protective measures. The human body, adapted for Earth's atmosphere, would fare poorly in the unforgiving cold of space. Without a spacesuit to insulate and pressurize, an astronaut's skin would cool rapidly, causing tissues to stiffen and blood vessels to constrict. This process mimics what occurs when frostbite sets in on Earth, but at an accelerated rate due to the vacuum's efficiency in removing heat. Yet the cold of space is not uniform. It varies depending on whether an object is exposed to sunlight or in shadow. In direct sunlight, objects can warm slightly above minus 150 degrees Celsius, though still far below freezing. This fluctuation between extreme warmth and intense cold presents unique challenges for spacecraft design, requiring systems that can manage both extremes. For instance, solar panels might become too hot when facing the sun, but freeze if they rotate into shadow. Engineers must balance these temperature swings to ensure equipment longevity and functionality. On Earth, we experience similar thermal fluctuations, yet our atmosphere buffers them, maintaining a relatively stable environment. In space, these variations are more pronounced and immediate. This stark contrast between Earth's protective blanket and the harsh realities of deep space underscores why space exploration requires such meticulous preparation. Each component of a spacecraft must be tested to withstand not just one extreme, but both extremes: heat from the sun and the cold void of shadowed regions. In the vacuum of deep space, objects do not radiate heat in a way that aligns with our earthbound experiences. Instead, they cool by emitting electromagnetic radiation known as Blackbody radiation. This process is governed by the temperature of these celestial bodies and their interaction with the cosmic environment. The cooler an object becomes, the longer wavelengths it emits, which are less likely to be absorbed back into itself, leading to a net loss of energy. This cooling mechanism operates on a principle that might seem paradoxical. Space itself acts as an infinite absorber rather than a thermal reservoir. Imagine a spacecraft floating in deep space. Despite the sun's immense heat at its core reaching millions of degrees Celsius, the craft would still cool down over time. This is because it emits radiation into the cold void beyond. The vacuum of space absorbs this energy without returning it, creating an environment where even the warmest objects eventually reach equilibrium with their surroundings. Now consider a neutron star, remnants of a massive stellar explosion known as a supernova. These celestial bodies are incredibly dense, packing more mass than our Sun into a sphere roughly 10 kilometers in diameter. Despite being born from such violent events, these stars gradually cool over billions of years. Their cooling is not due to active loss of heat, but rather the passive emission of radiation that stretches across the electromagnetic spectrum as they age. This process underscores how space's vastness and emptiness play a crucial role in determining thermal dynamics. The temperature of deep space is measured at approximately 2.7 Kelvin, just above absolute zero. This figure represents not a lack of energy, but rather an equilibrium state where radiation from all parts of the universe balances out. The cosmic microwave background, CMB, which fills this void, provides a faint glow that has been cooling since the Big Bang itself. Each photon emitted by stars, galaxies, and other celestial bodies contributes to this diffuse background, yet it is insufficient to warm space significantly. Blackbody radiation from these objects behaves in ways that challenge our understanding of heat transfer on Earth. For instance, while we might expect a warmer object to absorb more energy than it emits, in the vacuum of space, even moderately heated objects can lose temperature rapidly due to their emission rate exceeding absorption. This effect is particularly pronounced for smaller and cooler bodies like asteroids or comets, which can cool down faster than they gain heat from nearby stars. Understanding this phenomenon reveals how our Sun's intense radiation does not warm deep space. Instead, it contributes to the cosmic microwave background that permeates the universe. The photons emitted by the Sun travel vast distances before being absorbed by interstellar dust or other celestial bodies. This absorption process is part of a continuous cycle where energy moves through the cosmos, eventually reaching equilibrium across billions of light years. In this context, space remains cold not because it lacks heat, but because it provides no means to retain or recycle the energy it receives. Gravity wells around planets can trap heat and light, creating hotspots amidst cosmic coldness. In these regions, temperatures can vary dramatically compared to the -270 degrees Celsius of deep space. Consider Earth's orbit. It is a delicate balance between our planet's distance from the Sun and its atmosphere's ability to retain warmth. The average surface temperature on Earth hovers around 14 degrees Celsius, while just meters above the surface in the vacuum of low Earth orbit, temperatures can drop below -150 degrees Celsius. This stark contrast highlights how gravity wells function as cosmic thermoses, capturing heat within their depth. The Sun, a sphere of fusion at its core, radiates energy across vast distances. Yet, paradoxically, not all of this energy reaches the planets evenly due to the curvature of space-time caused by massive objects like Earth itself. The gravitational field around planets warps space-time, creating wells that can influence the path and distribution of photons from the Sun. These gravity wells are not just passive structures. They actively guide light and heat in specific directions, focusing them onto the surface. This phenomenon is akin to how a magnifying glass focuses sunlight, concentrating its energy at a single point. On Earth's surface, the atmosphere acts as a protective layer that traps heat through the greenhouse effect. However, in space, this trapping mechanism is absent. Here, objects cool by radiating their stored thermal energy into the void. The process of cooling in the vacuum of space can be likened to water evaporating from an open container on Earth. As molecules escape and diffuse into the surrounding environment, so too do photons from a warm object disperse into the cold expanse of deep space. This continuous emission of radiation results in rapid cooling for any object exposed directly to the cosmic void. Planetary surfaces are not uniformly heated. They experience temperature fluctuations due to their rotation and orbital dynamics. For example, on Earth, daytime temperatures can reach up to 50 degrees Celsius in some deserts, while nighttime temperatures can plummet below freezing. This variability is partly due to the uneven distribution of heat-trapping atmospheres around different regions of a planet. In space, this dynamic plays out at an even more extreme scale, with distant moons orbiting gas giants experiencing dramatic temperature swings as they move through and out of their parent planet's gravity well. The gravitational influence of planets not only shapes the path of photons, but also affects the distribution of cosmic rays. These high-energy particles are deflected by the magnetic fields generated within these wells, creating distinct patterns of radiation exposure around celestial bodies. This phenomenon is particularly evident in the case of Jupiter, where its immense gravity and complex magnetosphere trap cosmic rays, leading to a unique environment of intense particle bombardment near the planet's moons. The trapped heat and light in these regions create localized hotspots that stand out against the deep cold of space. While we often think of space as uniformly cold, the reality is far more nuanced. Within the gravity wells of planets, heat can be concentrated in ways that defy our expectations of an otherwise frigid cosmos. This concentration of energy within gravitational wells serves to maintain relatively stable temperatures on planetary surfaces, allowing for the existence of climates and ecosystems we recognize. In contrast, distant regions beyond these wells experience extreme cold, with temperatures plummeting as far as -270 degrees Celsius. The balance between these hotspots and cosmic coldness underscores the delicate equilibrium maintained by gravitational forces in our solar system. A billion years after the Big Bang, our universe was already colder than it is today, a counterintuitive fact given that stars had just begun to ignite. Each of these nascent stellar furnaces emitted light and heat, yet the void between them remained an icy expanse. This cosmic chill allowed for the delicate formation of early solar systems like our own, where dust and gas gradually coalesced under gravity's gentle pull. The temperature differential acted as a catalyst, drawing matter into dense clusters that would eventually birth stars. In this frigid environment, the universe was akin to an artist carefully laying down brushstrokes, each star system formed with the precision of a watchmaker assembling intricate gears. The coldness of space at that time is difficult for us to grasp, as it contrasts sharply with our experience on Earth. The cosmic microwave background radiation from those early times now registers at approximately 2.7 Kelvin, only slightly warmer than absolute zero. Yet within this near-absolute cold, the seeds of galaxies were sown. Imagine a place so vast and empty that even light itself takes millions of years to traverse its dimensions. These interstellar regions provided the perfect conditions for molecular clouds to condense, eventually leading to the birth of stars. The paradox lies in how such extreme cold facilitated the creation of intense heat. Within these nascent systems, gravity pulled matter into denser and denser configurations until nuclear fusion ignited, transforming hydrogen into helium in a flash of light and energy. As dust particles swirled through the early universe, they carried with them traces of elements forged in dying stars that predated our own sun. These stardust grains played an essential role in the formation of planets like ours, where iron from long-extinguished stellar cores now courses through veins and arteries. The chemical reactions that sustain life on Earth are a direct result of this ancient alchemy, linking us to the distant past of the cosmos. In these early solar systems, the dust clouds were not merely passive bystanders, but active participants in cosmic evolution, their presence influencing how stars would eventually form within them. These particles, each smaller than grains of sand you might find on a beach, contained histories older than any planet yet formed. The formation of the first stars marked a pivotal moment in the universe's history. Hydrogen and helium atoms came together with such force that nuclear fusion was initiated, releasing tremendous amounts of energy in the form of light and radiation. These early suns burned bright for only millions of years before their fuel ran out, collapsing into black holes or supernovae. The remnants of these violent deaths seeded the next generation of stars with heavier elements necessary for planet formation. Interestingly, this process was not uniform across all regions of space. Some areas remained relatively untouched, while others became hotbeds of stellar activity. This variation in star formation rates led to the diverse landscapes we observe today, from barren stretches of empty space to densely packed galactic clusters. In the context of cosmic time, 1 billion years is but an instant, yet it was enough for significant changes to occur within nascent solar systems. The early sun, still young and volatile, emitted more radiation than it does now, sculpting the protoplanetary disk around it with its powerful stellar winds. These winds cleared paths through the dust and gas, guiding the formation of planets and moons in a process known as accretion. The temperature fluctuations within this disk were crucial for the development of different planetary types. Volatile materials, such as water ice, condensed further from the sun, while rocky material aggregated closer to it. This arrangement laid the groundwork for the eventual diversity of terrestrial planets like Earth. The interstellar medium, where these early solar systems took shape, was a complex mixture of gas and dust that played host to countless interactions. Collisions between particles within this medium occasionally generated shockwaves capable of compressing nearby clouds into nascent stars. These shockwaves were often caused by the passage of supernova remnants or other energetic phenomena. The cumulative effect of these events over time gradually shaped the structure of galaxies, contributing to the intricate web of cosmic filaments we observe today. Each collision and interaction added a layer of complexity to the universe's narrative, weaving together threads of matter that would eventually coalesce into stars, planets, and life itself. In the intergalactic voids between galaxies, matter is so sparse that it appears as if the universe itself has been stretched to its limits. On average, there are fewer than 1 atom per cubic meter of space in these regions. This vast emptiness serves as a near-perfect vacuum, where heat dissipates without any medium to transfer it. Despite the sun's searing surface at 5,500 degrees Celsius and its corona reaching millions of degrees, deep space remains an icy void. The absence of particles means that radiation travels for billions of light years before encountering anything substantial enough to absorb or scatter its energy. This isolation amplifies the coldness, making it colder than any naturally occurring place on Earth. In this context, a single photon's journey through intergalactic space is akin to an explorer venturing into a desolate wilderness where no warmth awaits. The voids between galaxies are not mere empty spaces. They are active participants in cosmic thermodynamics. These regions act as reservoirs of coldness that help regulate the overall temperature of the universe. When matter eventually enters these voids, whether through the gravitational pull of nearby galaxies or due to the expansion of space itself, it cools rapidly. The process is so efficient that even stars and galaxies contribute minimally to warming the vast expanses between them. Consider this. In these intergalactic voids, if you were to place a thermometer inside a perfectly sealed, insulated container filled with the sparse gas present, it would read -270 degrees Celsius. This temperature approaches absolute zero, where molecular motion ceases entirely. Yet, paradoxically, the same forces that maintain this extreme cold also facilitate the eventual formation of new stars and galaxies as matter coalesces under gravity's pull. The vast emptiness is both a freezer and an incubator for cosmic structure. Intergalactic voids not only influence the temperature, but also shape the architecture of the universe. These spaces are expanding at an accelerated rate due to dark energy, further increasing their volume and reducing particle density. As voids grow larger and more numerous over time, they become even colder than before, contributing to a cooling trend across cosmic scales. This expansion is part of a grander narrative where the fabric of space itself is stretched thin, creating ever larger voids that act as reservoirs for coldness. In these vast expanses, time itself behaves differently from what we experience on Earth. The rate at which events unfold in intergalactic voids is not only influenced by temperature, but also by the curvature of space-time. For an observer within such a void, billions of years might pass before any significant change occurs, such as the formation of new galaxies or the collision of distant clusters. This slow evolution underscores the scale and patience required for understanding the universe's grand design. The coldness in intergalactic voids is not merely a passive state, but an active force that shapes the behavior of matter on cosmic scales. This pervasive chill can be likened to a deep freeze that preserves star-forming gases, which are slowly pulled into denser regions by gravity's gentle tug. Here, clouds of hydrogen and helium drift through space, their particles so far apart that they move in isolation for vast periods, sometimes thousands of light years, before encountering another atom or photon. These sparse interactions mean that the matter within voids remains pristine, unaltered by the energetic processes found near galaxies or stars. As a result, when these clouds do eventually collapse under gravity to form new stars and galaxies, they retain a chemical signature from the early universe, a time when cosmic microwave background radiation still permeated space. This untouched material contains the raw ingredients for stellar nurseries, where future stars will forge heavier elements through nuclear fusion. The process of star formation in such pristine environments is more efficient at generating light than heat. These nascent stars emit copious amounts of ultraviolet radiation that ionize nearby hydrogen clouds, creating glowing nebulae visible from great distances. Yet, paradoxically, the vast voids between these stellar cradles remain cold and dark, unaffected by the intense energy generated within them. The contrast is stark. While newborn stars blaze with light and heat, the immense spaces between them continue to cool further. Each new star formation event serves as a brief moment of warmth in an otherwise perpetually frigid expanse. The cycle of cooling and heating plays out over billions of years on cosmic timescales, contributing to the intricate dance of structure formation within the universe. In the far reaches of the universe, long after all stars have exhausted their nuclear fuel and ceased to shine, the cosmos will be an expanse dominated by black holes and dark matter. The remnants of stellar cores, these gravitational prisons, will hold within them the mass of entire galaxies, slowly radiating away any remaining heat through Hawking radiation over trillions upon trillions of years. This process is so slow that it defies human comprehension. Even as the universe ages, each passing second brings us closer to an inevitable cold and dark end where all energy has dissipated into the void. Yet, amidst this vast emptiness, dark matter continues to exert its mysterious influence, shaping cosmic structures with a force invisible to our telescopes. The black holes that will dot the future cosmos are not merely passive objects, but active transformers of spacetime itself. As they evaporate through Hawking radiation, their event horizons shrink and the gravitational pull intensifies, distorting the very fabric around them. This phenomenon is akin to an artist meticulously erasing their work, leaving behind a canvas that once held vibrant details. The paradox lies in the fact that while these black holes are consuming all nearby matter, they also emit radiation at the quantum level, a process so subtle it challenges our understanding of entropy and decay. In this deep future, entropy will reign supreme, ensuring that no form of energy can be preserved indefinitely against the relentless tide of heat dissipation. As stars cease to burn, the universe transitions into an era where light itself becomes scarce. Without new stellar formation to replenish photon emissions, the cosmos drifts further from thermal equilibrium with each passing eon. Dark matter, however, remains enigmatic in its role, neither emitting nor absorbing radiation that can be detected by our instruments. Its gravitational effects continue to sculpt galactic superclusters and voids, ensuring that even in this desolate epoch, cosmic architecture is not entirely abandoned. This interplay between dark energy and dark matter ensures the universe's expansion continues unabated, stretching these structures ever further apart until they become mere ghostly outlines against an increasingly uniform backdrop of cold, diffuse radiation. In contrast to the bustling activity of star formation and supernovae that have characterized the universe for billions of years, this future epoch is marked by profound isolation. Each galaxy cluster will be separated by distances so vast that the light from one would take eons to reach another. Within these clusters, black holes will reign as solitary monarchs, surrounded by clouds of dark matter and accretion disks of cold gas, if any remains. The universe's expansion accelerates this loneliness. Galaxies drift apart faster than they can interact, ensuring a future where the remnants of stellar life are forever beyond reach for each other. This vast isolation is not merely physical, but also temporal, as time itself dilates due to the accelerating expansion, stretching out the duration between cosmic events. The remnants of stars and planets will eventually become mere echoes in the grand scheme of things, their light long extinguished or redshifted into invisibility. The universe's age continues to increase exponentially, with each passing second marking another tick on a cosmic clock that stretches beyond human comprehension. In this distant future, our solar system may be but one speck among countless others, its fate irrelevant in the grand tapestry of universal evolution. Yet within this vast emptiness, there exists an inherent beauty in the simplicity and order that governs such systems, dictated by fundamental physical laws that have remained constant throughout cosmic history. As we peer into the deep future, it becomes apparent that our understanding of time is profoundly limited. The lifespan of the universe stretches far beyond any human conception, a span so immense that it challenges the very notion of existence itself. In this context, the brief moments of stardust and stellar life seem fleeting indeed, mere blips in an unfathomably long cosmic timeline. Yet, within these brief periods, complex systems like galaxies, stars, and planets form, evolve, and eventually dissolve into the void. This cycle of creation and destruction underscores the cyclical nature of cosmic processes, offering a humbling perspective on our place within this ever-evolving universe. In the near-zero temperatures of deep space, quantum fluctuations become significant phenomena, influencing how particles interact and behave far beyond our usual understanding of physics. At minus 270 degrees Celsius, these minute variations in energy are not merely theoretical constructs, but observable processes that shape the fabric of reality on a subatomic level. Quantum fluctuations can create fleeting pairs of particle-antiparticle entities known as virtual particles, which momentarily pop into existence before annihilating each other back into nothingness. This process occurs with such frequency and speed that it becomes a fundamental force in extremely low-temperature environments like the interstellar voids. The paradox here is that these ephemeral events are so commonplace at such temperatures that they play a crucial role in heat transfer across vast cosmic distances. Imagine, if you will, how this compares to the familiar warmth of a cozy blanket on Earth. While we experience thermal conductivity through material contact, in space, particles interact via these quantum phenomena, maintaining their low-energy states over unfathomable expanses. The energy released by these virtual particle interactions is minuscule yet essential for understanding how heat diffuses even across trillions upon trillions of kilometers. These fluctuations also influence the behavior of electrons orbiting atoms within the sparsest regions of space. At temperatures close to absolute zero, electrons exhibit quantum tunneling, a process where they pass through energy barriers that would otherwise be insurmountable based on classical physics alone. This phenomenon allows particles to traverse distances far greater than their typical thermal movement might suggest, leading to an interconnectedness at scales both microscopic and cosmic. In regions of space devoid of significant gravitational influence, these quantum effects become pronounced enough to alter the trajectories and velocities of free-floating hydrogen atoms. These atoms, which make up a substantial portion of interstellar matter, move in accordance with statistical probabilities rather than deterministic paths due to the pervasive nature of quantum fluctuations. This chaotic yet predictable motion underscores how deeply intertwined microscopic physics is with the grandeur of cosmic evolution. Despite being invisible to human eyes, these quantum processes have profound implications for understanding not only the coldest reaches of space, but also the origins and future of our universe. The behavior of particles at such extremes provides insights into fundamental questions about energy, matter, and the very structure of time itself. As we ponder this intricate dance of subatomic forces playing out across billions of light years, it becomes clear that even in the most desolate parts of the cosmos, there exists a rich tapestry of activity unseen by our everyday senses, yet vital to the fabric of existence. Consider for a moment how these quantum fluctuations manifest in the context of cosmic expansion. As space itself stretches outward at an accelerating rate, the energy density within it decreases, making conditions ever closer to absolute zero across vast distances. This cooling effect amplifies the significance of quantum processes, allowing them to dominate the behavior of particles over astronomical scales. In areas where matter is exceptionally sparse, such as voids between galactic clusters, these fluctuations become more pronounced, affecting not just individual particles, but entire clouds of hydrogen and helium gases. The pressure exerted by these virtual particle pairs can influence the formation of cosmic filaments, the vast web-like structures that connect galaxies across billions of light years. This intricate network is shaped partly by the delicate balance between gravitational attraction and the subtle quantum forces at play in near-absolute zero environments. Astonishingly, the same principles governing heat transfer via quantum fluctuations also contribute to the phenomenon known as cosmic microwave background radiation, residual warmth from the Big Bang itself that permeates every corner of the universe. This radiation provides a uniform glow across all directions in space, yet its temperature is just 2.725 degrees above absolute zero, a testament to how finely tuned these quantum effects are over cosmological timescales. In essence, what begins as an almost imperceptible shiver at microscopic scales becomes an architect of cosmic grandeur on the largest conceivable stage. In deep space, objects exchange energy through radiation alone, a process that defies our intuition of heat transfer as involving direct contact. This vacuum-mediated cooling means an object emits infrared radiation continuously, losing its thermal energy into the void without ever touching anything else. Yet, this same principle allows distant stars to warm planets light years away, their photons traveling freely across cosmic distances. The paradox lies in how efficiently space drains heat. An object emitting at room temperature would radiate energy so swiftly that it could cool to absolute zero if not continually supplied with new thermal input. This contrasts starkly with Earth's atmosphere, which insulates us like a thermal blanket. In space, the lack of air means no medium for conduction or convection, making radiation the sole pathway for heat loss. Imagine an astronaut floating in space. Their suit would radiate away body heat until they needed to activate heaters to maintain warmth. Consider this. While the sun's surface burns at around 5,500 degrees Celsius, deep space is a mere minus 273 degrees Celsius. The temperature gradient between these 2 points is so extreme that it underpins much of how our universe operates. Heat always travels from warmer to cooler areas, and in this vast cosmic furnace, the sun's energy is but one small spark among countless others. This gradient ensures that stars like ours are not only sources of light, but also engines driving the formation of planets, moons, and ultimately life. Spacecraft designed for deep space missions must account for this relentless cooling effect. They often feature multi-layer insulation, blankets to minimize radiation losses, and maintain equipment within operational temperature ranges. These layers can be as thin as a few micrometers, yet provide extraordinary thermal resistance. This technology reflects the sophisticated engineering needed to survive in an environment where temperatures fluctuate so dramatically from point to point. At absolute zero, atoms cease their random motion entirely, a state that remains theoretical but approaches it under specific experimental conditions on Earth. In space, objects are far from this idealized state, yet still exhibit behaviors that echo quantum principles at play even at macroscopic scales. For instance, the cooling of an object in the vacuum of space can be likened to a quantum phenomenon where particles lose their thermal energy without any physical collision. This process underscores how deeply intertwined classical and quantum physics are when it comes to understanding heat transfer. Intriguingly, this radiation-based cooling also plays a crucial role in the eventual fate of stars. Once stars exhaust their nuclear fuel and cease active fusion, they cool down by radiating away leftover energy. Eventually, white dwarfs like our Sun will dim into cold black remnants. This cooling process mirrors how any object in space loses heat, steadily over time, without the need for physical contact, with a cooler medium. Understanding this principle is key to grasping the life cycles of celestial bodies and the ultimate fate of the universe itself. Consider an astronaut floating in space, their spacesuit radiating heat into the void. Each square centimeter of exposed surface emits infrared radiation at a rate determined by its temperature. This constant emission of energy means that even though the sun is millions of kilometers away, its warmth diminishes rapidly as it travels through the vacuum. In this environment, the astronaut would feel no wind chill or convection currents to cool them further. Instead, their body heat escapes purely through radiation. The cooling effect is relentless and efficient, a stark contrast to Earth's atmosphere where thermal energy can be trapped or distributed by air movement. This phenomenon has profound implications for spacecraft design, as engineers must carefully balance the need to radiate excess heat from sensitive electronics with the equally pressing concern of retaining warmth in critical systems. In space, maintaining the right temperature equilibrium is a delicate dance between generating and dissipating energy. For instance, solar panels on satellites convert sunlight into electricity, which then powers heaters to counteract the cold. This balancing act ensures that equipment functions optimally despite operating under conditions where heat transfer occurs exclusively through radiation. The efficiency of this cooling process also highlights the fundamental role it plays in shaping cosmic structures over vast timescales. Stars like our Sun will eventually lose their radiant energy into space, cooling down until they become dark stellar remnants. This slow dissipation of energy is a key factor in how galaxies evolve and change over billions of years. On the surface of a comet, far from Earth's familiar warmth, one encounters an environment where extreme cold and intense heat coexist in a delicate balance. The temperature hovers around -200 degrees Celsius, yet it can spike to over 300 degrees Celsius when the comet passes near the Sun. This fluctuation is not gradual but sudden, akin to switching between a deep freezer and an oven. Imagine standing on this icy surface. Your boots sink slightly into the porous ice, which holds pockets of gas within its crystalline structure. The sublimation process turns solid ice directly into vapor without passing through a liquid state, a phenomenon that would make even the most advanced refrigerators envious in their efficiency. Yet, paradoxically, the Sun's radiation can reach temperatures so high that it would melt any surface not shielded by a thick layer of gas or dust. As you stand there, the comet hurtles through space at speeds reaching 50 kilometers per second relative to Earth. This velocity is faster than any man-made object in our solar system, save for a few specialized probes and spacecraft designed specifically for such missions. The sensation of being stationary while your surroundings move at thousands of miles an hour creates a peculiar disorientation. Your body, however, remains stable, insulated by the comet's cold surface, which absorbs most of the radiant heat from the Sun. The surface you stand on is not static, but constantly changing. As the comet approaches the Sun, its ices begin to vaporize, creating a thin atmosphere that trails behind it like a tail of dust and gas. This process is known as outgassing, where volatile substances escape the comet's surface due to solar heating. Each molecule that leaves contributes to this tenuous envelope, which can stretch for thousands of kilometers. In contrast, on Earth, such rapid changes in atmospheric composition are rare and occur over geological timescales. The light from the sun, when it reaches your eyes, appears brighter than any sunrise you've ever witnessed. It is not just a question of intensity, but also color. The ultraviolet radiation causes molecules in the atmosphere to fluoresce, producing an array of colors that can be dazzling. Yet this same light, which seems so powerful and warm from a distance, is responsible for the extreme cold on the comet's surface. The ice acts as a near-perfect reflector of infrared radiation, bouncing most heat back into space before it has a chance to warm your boots. Despite the harsh conditions, life has found ways to thrive in similar environments here on Earth, such as inside Antarctic dry valleys or beneath glaciers. These extremophiles are adapted to survive in places where liquid water is scarce and temperatures plummet well below freezing. The survival mechanisms of these organisms offer clues about how life might exist elsewhere in the universe, even in places as inhospitable as a comet's surface. As you stand there, the thought that microscopic life could be clinging to the icy grains around your feet becomes almost tangible, bridging the gap between this alien landscape and our own planet. In the vacuum of space, where matter is scarce and distance is vast, temperatures hover around -270 degrees Celsius. This coldness is not merely a result of the sun's distant glow, but is influenced by an invisible force, cosmic background radiation, which permeates every corner of the universe. Despite its ubiquity, this radiation contributes little warmth to our surroundings. Instead, it serves as a reminder of the Big Bang's aftermath, when the universe was filled with intense heat. This radiation, now cooled to microwave frequencies, is so faint that detectors must be shielded from Earth's own radiative noise to measure it accurately. Yet, in some ways, this radiation is more pervasive than any form of light we can see. It stretches across an area equivalent to a sphere with a radius of 13.8 billion light-years, our observable universe. This vast expanse suggests that the same background radiation that warms the space between galaxies also bathes every square centimeter of Earth's surface, though it contributes negligibly to our planet's warmth. In interstellar regions, where matter is sparse and collisions rare, cosmic background radiation acts as a gentle reminder of the universe's origins. It doesn't warm because its energy is spread out so thinly across such a colossal volume. To illustrate this, imagine each photon as a tiny messenger carrying information about the early universe, each one traveling countless light years to reach us, their combined efforts still too feeble to noticeably heat an astronaut's spacesuit. Yet, for all its vastness and ancient origins, cosmic background radiation remains undetectable without sophisticated instruments. Its presence is inferred from its effects rather than directly felt in any tangible way. It contrasts starkly with the sun's glaring light and intense warmth. While the sun burns at millions of degrees Celsius in its core, this ancient glow does little to change the near-absolute zero temperatures between stars. The radiation's uniformity across the sky measured by satellites like COBE and WMAP, reveals a universe that was once incredibly uniform. This smoothness implies an early era when matter was evenly distributed, before gravity could pull it into clumps we now call galaxies. In this context, cosmic background radiation becomes not just a cold echo of the past, but also evidence of how our universe evolved from a simple, hot state to its current complexity. On Earth, where temperatures are moderated by atmospheric interactions and solar radiation, the concept of such pervasive yet indifferent heat might seem foreign. But in space, this radiation is a constant presence, affecting every particle it encounters. It interacts with dust particles floating between stars, sometimes nudging them slightly, but never enough to warm anything significantly. This subtle influence underscores how the universe's most profound processes are often invisible and silent, shaping our cosmos without fanfare. The cosmic background radiation, though omnipresent, behaves like a persistent but faint hum in the vast concert hall of space. This radiation is so diffuse that it carries less energy than the weakest whispers of static on an old television set. Yet its reach extends far beyond the boundaries of our galaxy, affecting every point in the observable universe equally. If one were to travel through deep space, this radiation would remain constant, providing no relief from the extreme cold. In regions where stars are densely packed, such as near the center of galaxies, the background radiation is overshadowed by the intense light and heat emitted by these stellar giants. But away from these luminous hubs, in the vast cosmic wilderness, it reigns supreme, a relic of a time when the universe was far hotter and denser. The energy carried by this radiation is spread so thinly that its impact on individual particles or objects is negligible. For instance, if you were to measure the temperature increase caused by cosmic background radiation over years of exposure in deep space, it would be imperceptible. This paradoxical scenario, where an omnipresent force has such a minimal effect, demonstrates how our universe operates at scales far removed from our everyday experiences. On Earth, heat is often transferred through physical contact or air currents, but in the vacuum of space, where matter is scarce, this radiation becomes a reminder of the vast distances and empty spaces that separate cosmic entities. Each photon from the cosmic background has traveled billions of years to reach us, yet its effect on any given location in space is so minimal it would take an eternity for it to noticeably warm even the tiniest speck of dust. At the boundary where Earth's magnetosphere meets outer space, particles encounter a sudden transition from relatively warm to exceedingly cold environments. This demarcation is known as the magnetopause, a dynamic frontier shaped by the interplay between solar wind and our planet's magnetic field. Here, temperatures can plummet dramatically within mere kilometers, creating an environment that challenges our understanding of heat transfer. Just beyond this threshold, electrons and protons from the solar wind abruptly cool down to near absolute zero. This rapid drop in temperature is a result of particles no longer being confined by Earth's magnetic embrace, and thus radiating energy freely into the void. Remarkably, these particles are now colder than temperatures found even at the poles on our planet, where winter can push limits but never quite reach such extremes. Yet this frigid zone also acts as a shield, deflecting solar wind from directly bombarding Earth's atmosphere. At the heart of this transition lies the concept of adiabatic cooling, a process familiar to mountaineers who experience temperature drops with altitude gain. As particles move further away from Earth's magnetosphere, they spread out and lose kinetic energy in the form of heat, much like a gas expanding into an empty chamber. This cooling effect is so pronounced that it defies our usual expectations about how space should feel, given its association with the blazing sun nearby. For an astronaut floating just beyond this boundary, the sensation would be akin to stepping out of a warm bath and entering an icy freezer. Yet, within this cold expanse lies a paradox. While temperatures drop sharply here, the surrounding vacuum is utterly devoid of substance for heat conduction or even radiation to interact with. This creates what might seem like an impossible situation. Particles are incredibly cold, but also isolated from any medium that would allow them to exchange energy in ways familiar on Earth. This isolation means that particles at this boundary remain cold and static, not due to cooling alone, but because they have no means of exchanging heat with anything else. Farther into space, beyond the magnetopause, a different kind of dynamics takes hold. Here, the solar wind continues its journey unimpeded by Earth's magnetic field, carrying away some of our planet's charged particles in what is known as plasma sheet erosion. This process strips electrons from atoms and molecules, creating a trail of ionized matter that drifts into interplanetary space. Each particle lost represents a tiny fraction of Earth's atmosphere, contributing to the gradual thinning of our protective layer over time. Returning to the immediate boundary, it becomes clear that this region is not just a simple transition, but a complex dance between solar influence and planetary magnetism. The magnetic field lines act like invisible threads, guiding particles in one direction while repelling others. This delicate balance ensures that Earth remains protected from harmful radiation while still exchanging some of its own material with the cosmos. In essence, it's a testament to how our planet interacts not just within itself, but also as part of an interconnected cosmic system where boundaries are fluid and ever-shifting. Imagine standing on a hilltop at night, gazing up at the starry sky. Each breath you take exchanges heat with the cooler air around you, a familiar process that maintains Earth's thermal balance. This exchange is part of our planet's intricate climate system, which relies heavily on the vast emptiness of space to act as an infinite heat sink. Space absorbs heat from Earth without returning it, helping regulate global temperatures by cooling the atmosphere and oceans. This relationship between Earth and deep space is akin to a thermostat in your home. Just as a thermostat controls indoor temperature by releasing warm air outside during winter, Earth releases its excess heat into the cosmos through radiation. The vacuum of space acts as an insatiable sponge for this energy. Unlike on Earth, where heat can circulate among land, sea, and atmosphere, deep space offers no medium to trap or recycle that warmth. In fact, at -270 degrees Celsius, it is so cold that all objects in the vicinity inevitably lose their heat. To grasp how effective this cosmic heat sink is for our planet, Consider Earth's average surface temperature, roughly 14 degrees Celsius. Now imagine if there were no space to cool us down. The greenhouse effect would intensify dramatically, leading to a runaway heating scenario where trapped heat accumulates endlessly. Yet, because of the vacuum's insatiable demand for energy, Earth can maintain relative stability. This process has been ongoing since the planet's formation, ensuring that our climate remains within livable parameters. Heat dissipation from Earth occurs primarily through long-wave infrared radiation. As molecules on Earth vibrate and release energy, these photons escape into space where they are never returned. This continuous outflow of heat is crucial for regulating global temperatures, preventing a buildup that would otherwise make life unsustainable. Interestingly, this process also affects the timing of seasons. During summer, more solar radiation reaches the poles than in winter, yet it's the cold vacuum of space that ensures polar regions don't overheat. The efficiency with which Earth sheds its heat into deep space is remarkable when compared to alternative scenarios. Were Earth to be surrounded by a dense medium like gas or liquid, even at low pressures found high in our atmosphere, thermal equilibrium would occur much more slowly. Instead, the vacuum allows for rapid energy loss, maintaining temperatures that support life as we know it. This underscores how fundamental the emptiness of space is to planetary habitability. In this context, consider a hypothetical scenario. What if Earth were encased within a thin shell of atmosphere extending far into space? Without the vast emptiness beyond this shell, heat would accumulate and redistribute differently across our planet's surface, potentially leading to extreme climate fluctuations. The current arrangement ensures that thermal equilibrium is maintained on a global scale, allowing for stable weather patterns and sustainable ecosystems. This dependency on deep space as an unyielding repository of excess planetary energy underscores the delicate balance that sustains life on Earth. The continuous flow of heat from Earth into space is not only crucial for maintaining global temperatures, but also plays a vital role in driving weather patterns and ocean currents. As infrared radiation escapes our atmosphere, it interacts with greenhouse gases like carbon dioxide and water vapor, which absorb some of this energy before releasing it back down to the surface or radiating it further into space. This complex dance of heat transfer fuels atmospheric convection cells, large-scale air movements that help distribute warmth across the globe. For instance, warm air rises from equatorial regions, cooling as it ascends, and then sinking at higher latitudes, creating a cycle known as Hadley circulation. Without this process, equatorial regions would become even hotter, while polar areas could freeze in perpetuity. The vacuum of space acts as both an endpoint for these energy flows and a catalyst for Earth's dynamic climate system. In contrast to the rapid cooling provided by the void of deep space, heat transfer within Earth's atmosphere is comparatively sluggish due to convection, radiation, and latent heat from water vapor condensation. This contrast highlights how the extreme coldness of space accelerates the dissipation of terrestrial warmth, facilitating a more stable climate balance. To illustrate this point further, consider a scenario where Earth's distance from the Sun were altered slightly. shifting its position within the habitable zone. In such circumstances, the efficiency with which heat escapes into space would be critical in mitigating potential runaway greenhouse effects or ice ages. The vacuum serves as an essential buffer against these extremes. This delicate interplay between Earth and the cold expanse of deep space demonstrates how finely tuned our planetary climate system is to its cosmic surroundings. Without this vast, frigid backdrop, life on Earth might struggle to maintain the stable conditions necessary for survival. The universe, born in an explosion of unfathomable energy, began as a near-infinite plasma hotter than any star. Yet, today, deep space has cooled to temperatures just 3 degrees above absolute zero. This cooling process, spanning billions of years, has shaped galaxies and stars into the structures we see today. Imagine this vast cosmic chill. Every photon from the early universe's glow is still traveling through the void, its energy redshifted by the expansion of space-time. The first stars were beacons of light amidst an otherwise opaque plasma, their formation a delicate balance between gravity pulling matter together and radiation pushing it apart. This era, known as recombination, occurred around 380,000 years after the Big Bang, when protons and electrons combined to form neutral atoms, allowing photons to travel freely for the first time. Yet, in this cooling universe, pockets of denser matter began to collapse under gravity's pull, igniting the nuclear fires that would become stars. It is a paradox. As the universe expanded and cooled, it set the stage for stellar birth. In these nascent galaxies, stars form through intricate processes involving dust clouds and molecular gases swirling in protoplanetary disks. Each star's life cycle depends on its mass. Smaller ones burn more slowly, while massive stars live fast and die young. 1 billion years after recombination, our universe had already begun to cool further, a counterintuitive fact given that trillions of new stars were lighting up the cosmos. The temperature gradient between these nascent galaxies and the intergalactic voids is critical for understanding how galaxies grow through mergers and accretion of gas. This cooling trend influences star formation rates across cosmic time. Consider the fate of our own galaxy, the Milky Way. It formed from a network of smaller structures that merged over billions of years, each contributing to its current state. The rate at which new stars are born in galaxies has decreased dramatically since the universe's early days. This slowdown is due not only to the exhaustion of gas reservoirs, but also to the increasing prevalence of older, less active galaxies. As stellar nurseries cool and star formation wanes, galaxies begin to resemble collections of aging stars rather than dynamic crucibles for cosmic creation. In deep space, objects exchange energy through radiation alone, a process that defies our intuition of heat transfer as involving direct contact. This method of cooling is crucial in understanding the life cycle of stars and the evolution of their host galaxies over time. When a star dies, its remnants, neutron stars or black holes, are often left behind, surrounded by expanding clouds of gas and dust enriched with heavy elements produced through nuclear fusion. These leftovers are essential for future generations of stars and planets. The cooling universe thus provides a stage for cosmic recycling, ensuring that the building blocks of life persist even as the heat of creation fades. The cooling universe has also led to the formation of exotic objects like white dwarfs and black holes. A white dwarf, the remnant of a low-mass star like our Sun, cools over billions of years, eventually reaching temperatures so low they no longer emit visible light. This process takes place in a timescale that is almost inconceivable. For instance, a white dwarf may take trillions of years to cool from its initial 10,000 Kelvin down to near absolute zero. Meanwhile, supermassive black holes at the centers of galaxies grow through accretion events, where material spirals inward and emits intense radiation before vanishing beyond the event horizon. These processes highlight how cooling affects not just star formation, but also the evolution of entire galactic systems, shaping the universe we observe today. Within deep intergalactic regions, temperatures hover around -270 degrees Celsius, creating an environment where even atoms move with minimal kinetic energy. This coldness is not uniform. It fluctuates subtly due to interactions between cosmic microwave background radiation and dark matter. The cosmic microwave background, CMB radiation, a remnant from the Big Bang, permeates every cubic centimeter of space. Yet, its interaction with invisible dark matter introduces subtle variations in temperature across vast expanses of the universe. These fluctuations are so minute that they would be imperceptible to human senses, but have profound implications for cosmic thermodynamics. Consider this. While CMB radiation bathes all points in the universe with a nearly uniform -270 degrees Celsius, dark matter particles, though elusive and non-luminous, do interact weakly with ordinary matter. This interaction, though faint, can cause slight deviations in the otherwise homogeneous CMB temperature map. These variations, known as anisotropies, are crucial for cosmologists to understand how galaxies formed from tiny density fluctuations in the early universe. The human-scale analogy would be akin to noticing a barely perceptible breeze that subtly shifts your hair's direction on a windless day. In regions where dark matter is more densely concentrated, such as around galaxy clusters, these temperature deviations are amplified slightly. These areas act like gravitational wells, attracting both visible and dark matter. As a result, the cosmic microwave background radiation passing through these dense regions experiences minuscule changes in its path and energy distribution. This process, known as the Sunyaev-Zeldovich effect, provides astronomers with valuable information about the large-scale structure of the universe without directly observing dark matter itself. It is as if we could infer the presence of a hidden ocean by measuring how it ripples across an otherwise calm surface. At the heart of this interaction lies the peculiar nature of dark matter. Unlike ordinary matter, which interacts through electromagnetic and strong nuclear forces, dark matter particles are thought to interact primarily through gravity. This weak interaction means that while it exerts significant gravitational influence on cosmic structures, its thermal effects on radiation are minimal yet detectable. Imagine a vast auditorium filled with soundproof panels. Though the acoustics dampen most sounds, they still allow for subtle changes in volume and pitch depending on where you stand. These temperature fluctuations trace back to the earliest moments of the universe, when tiny quantum fluctuations grew into the large-scale structures we observe today. The seeds of galaxies, clusters, and voids were sown during this epoch, with dark matter playing a pivotal role in their development. As radiation from the Big Bang cooled over billions of years, it left an imprint on the universe's structure through these minute temperature variations. This process underscores how even the most subtle interactions can have profound consequences across cosmic scales. Despite being invisible and interacting only weakly with ordinary matter, dark matter's influence is pervasive throughout the cosmos. It shapes galaxies, clusters, and voids by providing additional mass that attracts visible matter. The interaction between CMB radiation and dark matter illustrates the intricate web of connections in our universe, where even the faintest signals carry significant information about its history and structure. As we observe these minute temperature fluctuations today, we are essentially peering into the origins of cosmic architecture itself. In Earth's atmosphere, heat is trapped through a process known as the greenhouse effect, where gases like carbon dioxide and water vapor absorb and radiate infrared radiation back towards the surface, keeping our planet habitable. This delicate balance contrasts sharply with the environment of deep space, where temperatures are approximately -270 degrees Celsius, colder than any naturally occurring place on Earth. The molecules in our atmosphere vibrate and collide constantly, transferring heat through conduction and convection, whereas in space, such molecular interactions are virtually non-existent due to the near-total absence of matter. This disparity becomes particularly evident when we consider how energy is exchanged between objects in both environments. In deep space, energy transfer occurs exclusively via radiation, a process that requires line-of-sight contact. This means that any object exposed directly to the vacuum of space radiates its heat away into the void until it reaches thermal equilibrium with its surroundings, about -270 degrees Celsius. Meanwhile, on Earth, an average temperature of around 15 degrees Celsius is maintained through a complex interplay of atmospheric gases and surface materials. It's remarkable that both environments can exist in such stark contrast, yet they are fundamentally connected by the principles of thermodynamics. The thermal insulation provided by Earth's atmosphere is crucial for life as we know it. Without this protective layer, the temperature fluctuations on our planet would be extreme, making survival nearly impossible. In deep space, however, any surface exposed to the vacuum cools rapidly until its emission spectrum matches that of the cosmic microwave background radiation. This process can occur in a matter of minutes for an unprotected object, highlighting just how quickly heat dissipates in such conditions. The contrast is not merely one of temperature, but also of complexity. Earth's atmosphere requires continuous dynamic processes to maintain equilibrium, while space reaches thermal stability through its simplicity and emptiness. A fascinating aspect of this difference lies in the behavior of materials in these environments. In Earth's atmosphere, materials expand when heated and contract when cooled due to changes in molecular spacing. However, in deep space, where temperatures drop to -270 degrees Celsius, the molecules are so far apart that they barely interact. This near absence of molecular collisions means that thermal expansion or contraction is not experienced in the same way. Instead, materials exposed to the cold vacuum of space can experience a phenomenon known as outgassing, wherein volatile compounds within them vaporize and escape into the surrounding environment. The absence of air pressure in deep space accelerates this process, leading to a gradual depletion of such compounds. Returning to our consideration of temperature extremes, it is worth noting that while -270 degrees Celsius seems incredibly cold, there are places on Earth where temperatures can be even colder, though only briefly and artificially. For instance, laboratories on Earth have managed to achieve temperatures as low as -273 degrees Celsius through advanced cooling techniques such as laser cooling of atoms. This is a mere 3 degrees above absolute zero, the theoretical temperature at which all molecular motion ceases. In contrast, the natural coldness of deep space, while vast and seemingly eternal, never quite reaches this level of frigidity. Yet it remains a constant reminder of how much our planet relies on its atmosphere to shield us from such extreme conditions. In conclusion, the stark difference between Earth's warm blanket of air and the icy vacuum of space is a testament to the delicate balance that sustains life on our planet. As we observe the near-zero temperatures in deep space, we are reminded of how fragile this equilibrium truly is. The contrast highlights not only the physical properties of these environments, but also underscores the complexity and resilience required for life to flourish. Just as the opening image hinted at the extreme cold of deep space, we now understand it better through its connection to our own atmosphere's role in maintaining Earth's temperature, a crucial difference that keeps us warm amidst an otherwise frozen cosmos. At -270 degrees Celsius, deep space cradles us in its vast, frigid embrace, reminding us of how small and yet how protected we are. The journey through the cosmos draws to a gentle close tonight. Thank you for being here with me under this blanket of stars. If you enjoyed your cosmic sleep, feel free to subscribe and leave a like. Good night, and may the tranquility of space guide you to peaceful dreams.